Okay, so chapter 5 deals with volumes of revolution and using integration to find these results. Okay, so let's just remind ourselves of how to find the area under the curve, using integration. So if you imagine this is part of your function, say y equals f of x, then if you want to find the area between the two lines x equals a and x equals b, you can integrate the function between these two limits, and that will be the area. So it's f of x dx, or you could put y dx. So you can extend this idea for the volumes of revolution. So imagine here's my curve again, let's call it y equals f of x, and we want to find the volume of the revolution of this. If you imagine this laminar section under the curve, so and we have the area, it's going to be rotated around the x-axis. There's my x-axis, there's my, and you're going to get a shape. Let me just draw it as much as I can. There you go. Okay, so you effectively, it's going to be a bit like a vase or a 3D shape that you are going to get. Imagine spinning it around the x-axis, and then visually what you will see is that 3D object. Now, it can be used a lot in modeling, because when you do integration, you'll be able to find the exact volume of this shape. So why does it work? When you learn about integration from first principles, it's the idea is that you're breaking up each section between x equals a and x equals b into tiny cylinders. So here, if you imagine just this in here, let's break it up. Imagine breaking it up into tiny strip here, which is of thickness delta x, and as that delta x gets smaller and smaller, this little strip will become closer and closer to a rectangle, which is delta x times the y coordinate of the point here, which is f of, let's say f of x. It will be of a point there, it doesn't matter. But effectively, as this strip gets smaller and smaller, you will get the area of the tiny pink rectangle here, and the integral symbol reminds a letter S for some of these little strips. Okay, so there'll be loads of them. So if you think about the volumes of revolution, so imagine like they just cut a little section somewhere between A and B of thickness delta x, which is tiny. I've drawn it quite thick, but that section is going to be quite tiny. There we go, just do that. What we're going to do is imagine spinning it around. There you go. And you're going to get this effectively like a cylinder. So I've done it as much as I can. There you go. So it's spinning around, and you are going to find the volume of that one cylinder. As the delta x gets smaller and smaller, this cylinder gets thicker and thicker, and you will have loads of them, infinite number, as delta x gets smaller, and the integration deals with it. Now, what's the volume of one of this cylinder? Well, it's going to be, so one cylinder, if you imagine, it's going to be the area of the cross section, so one of the circles, so it's pi r squared, let's call it r for now, and then multiply by the height or the depth, which is delta x. Now it's pi. Now r in this instance is going to be your value of a function f of x at that particular point. So let's just general point will be f of x. There you go, delta x. So as the idea of integration is that you're making those thickness of each cylinder smaller and smaller, and you are allowing to have a sum of loads of those cylinders. Okay, so effectively you are going to get pi. Now let's call it y. I'll do f of x first, and then it'll be easier to remember when it's replaced with y. Now we say dx, not delta x. Okay, so the way you might want to remember it, that you put pi in front of it, and then you put y squared dx. Okay, so this is between x equals a and x equals b. Okay, so it's very similar to the area of a circle, where radius is your y coordinate, and then dx symbolizes the fact that it's integration, and that is the this tiny little thickness of each cylinder that you are dealing with. So this is just a gist of it. Okay, but in order to be successful in answering questions on volumes of revolutions, by the way, the volume you're getting is called the volume of revolution because you are revolving it around the x-axis, rotating it. You don't really need to know exactly why that particularly works, just know how to apply it. So let's do the first question. Example 1. You've got the function y equals 9 minus x squared. It's already drawn for you, so it's your upside down quadratic, if you like. We are going to find let me just check what it says. I presume it's going to be this part here is going to be rotated around the x-axis by through 360 degrees, or 2 pi, which is the same thing. So first of all, as soon as the question mentions rotation, volumes of revolution around the x-axis, quote the formula. So we'll put x here because that tells me that I'm rotating around the x-axis. So it's pi, and then you've got the integral between the two limits. Let's call them a, b, and it's going to be y squared dx. Okay, so this is the general formula. So I know what y is. It's 9 minus x squared. I know what a is because a is going to be 0. This is my lower limit, and b is over here. So I need to find that upper limit. To find that upper limit, I'm going to find the roots of that equation. So when y is equal to 0, so it's x squared is equal to 9, giving me x is equal to plus or minus 3. So clearly minus 3 would go here, so b is equal to 3. So this is my upper limit. So let's just pop those results into the formula. So it's pi, and the lower limit here is 0, the upper limit is 3. Y squared is 9 minus x squared all squared. Okay, so now it's just the mechanical integrating that needs to be done. So let's prepare it for integration. Expand it. 81 minus 18x squared plus x to the power 4 dx. So let's just integrate 81x minus 18x cubed over 3 plus x to the power 5 over 5 between the limits 0 and 3. Okay, put the limits in. So it's 81 times 3 minus, either leave it as 18 over 3 or work it out as 6 times 3 cubed plus 3 to the power 5 over 5 minus the lower limit here is going to give me, if I put 0 into that, just 0. Okay, so let's use a calculator to work it out. So it's going to be 81 times 3 minus 6 times 3 cubed plus 3 to the power 5 divided by 5. Obviously, if I had to evaluate this limit, if I knew it wasn't 0, I would be using ANS key and then changing the input. So it's 129.6 pi, or 648 pi over 5. Now if you want it as a, it might be that it will be appropriate to do this. It's times by pi, 407 cube units to 3 significant figures. There you go. So it depends what the question asks us to do. So let's now have a go at exercise 4a, all about volumes of revolution around the x-axis.